Is this clear? Is this clear what I'm trying to do over here? Yes.
Is it okay to treat, when you have zeros in the first and fourth boxes to take the place of, to give value as you shift left and right? Is it okay to set that? Are you expecting that, I guess, to set a 0? Or
We don't have enough switches, and that's why I haven't, I'm asking you guys to set it to a specific value. But you can have, what it basically is doing is giving you a way to get serial data and put it and store it in the memory.
Okay. So it's because we're limited with the number of switches.
Yeah, it's the limitation of the board because of which I'm asking you to do this. Otherwise, if you see the number of ports you would need is 1, 2, 3, 4, 5, 6, 7, 8, 9. We have just 8 switches. So that's why I'm just putting a value of 0. And that's why I say that initially give a 1, 1 to set a specific output, and then you can see the LEDs moving to the left and the right and things like that. Okay? Is this clear? Please ask questions. Okay, I guess it's clear then. Yes.
If like some problems that we need going to ask us like doing the same thing, adding a 1 instead of 0, like on the left, on the right. I mean, why is that? Can that happen? Or
Yes.
like,
You can give any input over here. You can connect this to a specific line and provide a series of bits on that, 1, 0, 0, 1 and stuff like that. It's just that what would happen is if I provide an input, say I prime over here, which has an input maybe say 1, 0, 1, 0, 1, 0 or something like that. Okay? And if these two lines are set up to a 1, 0, that means it's doing a left shift. Instead of this 1, 0, instead of this 0 appearing, 1, 0 is
So it's the far right 0 you're looking
oh,
at.
sorry, this is connected to line 1. Yeah, so it's 0, 1, it's doing a right shift. 0, 1, it's doing a right shift. Instead of this 0, you would get the first bit, which is 1. If I do a 0, 1 again, the next bit appears. Now this one will move over here now. And that 0, which is the next bit, will appear over here. And if I do another 0, 1 now, and a rising edge, the next one appears. So this 0 moves over here. This one moves over here, this one moves over here. And the next bit 1 comes in here. I do another one, and so you've taken a serial data 1, 0, 1, 0, and now you have stored it in the memory. That is a D flip-flop. That is 0, 1, 0, 1. If you see 0, 1, 0, 1, up 4 bits. Okay. If you wish to make any of these observations, you can either connect it to your left shift or your right shift because we're limited by just 8 switches. So what you can do is just connect to one of them and then test it accordingly. But tell me if you want to do any of those things because you have to change the UCF5 which I provided to you guys. So we'll have to make changes in the entity and the UCF5. So you'll need my help with that. So let me know if you want to go ahead and test something like that, providing serial data and seeing that it appears at the output. Okay? Let me know. If you don't want to do any of those things, you can simply go ahead and provide an input of a 0 bit over here. And follow these sequence of steps to observe some sort of a change in the output. Okay? Is this clear? Okay. Now comes the fun part.
Slightly off topic. I'm sorry. Could you, if you wanted to, could you set the push buttons?
The push buttons have the property that As long as they're pressed, they give the input of 1,
Okay,
and when you release them, they give an output of 0.
okay.
So there is no, you cannot set it to become a constant value. By default, it is in the off state, which is 0. So you can use it, but it's just that every time you want a 1, you have to press and hold on to it. You cannot press and then just leave it and it stays in the press state. That's the only difference between a button and a switch.
I'm trying to get this done this weekend
Yeah. Are you working on it today?
So this is basically your
after
code.
lab.
By default, it has a code that is running on it, and it alternates between outputting a pass and 128. That's basically a state machine that is being implemented over there. One state gives an output of pass, the other state outputs 128. You can provide outputs to these flip-flops, these 7-bit displays too. But if you want to do any of those experiments, read the digital in board, and again you have to change the UCF file, so contact me if you want to do any of those experiments. Is this clear to everyone what it looks like? Mostly clear. Okay. Now, you have to connect your board with the computer through this mini USB port. It is right next to the serial cable wire that you have over here. Serial cable input that you have over here. Connect the mini USB part of the wire over here, and the other end of the USB goes into your computer. Obviously, you have to switch on your system. The switch button is up here. Okay, if you don't switch it on, it's not going to detect it. As soon as you switch it on, these two LEDs should light up. One of them is these two. One of them is red in color, the other is yellow in color. Now, yeah, and there are some really cool things that happen over here. When I press this button, it does something like that. You press this, it does that. So, it basically goes around and then appears as a 9 and a dot. That's again another state machine that is implemented in there. There is a reset button up here. When you press that, it goes back into the default state that it was. No matter where it is, that's almost like a reset button for the entire board. So it goes into the initial state that it was in, and that is basically a pass and a 128. You have the switches, you have the LEDs. In the universal shift register problem, I've asked you guys to use switch 0, 1, 2, and 3 as your inputs, the parallel input, switch 5 as your clock, and switch 6 and 7 as your select lines. To provide a rising edge on the clock, someone was asking me that question, how to provide the rising edge on the clock. You literally, in the down state, the switches, which are how they are configured right now, it basically has a value of 0. And when you push the switch up, you're literally providing a rising edge by pushing the button up, because now you're making it equal to a 1. And that's how you would provide your rising edge on the clock. So in the current program, when I push it up, the LED lights up. I don't know if, yeah, you can see it. So an LED lights up if it has an input of 1. It shuts down if it has an input of 0. Currently, by default, the program that is programmed onto this FPGA makes the LED light up whenever the corresponding switch is switched on. And it's really cool the way the LEDs go off. They don't go off immediately. They actually fade away. So that's something to do with analog and things like that. You don't have to worry about it. So that is the basic setup. You will be using these LEDs and these switches. The UCF file which I provided to you guys, what it does is it connects the ports on the entity with corresponding hardware that should be controlling those ports. So each and every one of them, I don't know if it's clear right now, but if you have your boards with you, you can see that each and every LED has a letter and a number corresponding to it. Each and every switch, you cannot see because of the shadow, but over here, they have numbers corresponding to each and every switch. The UCF file corresponds a port to a switch or an LED and things like that. In this case, all the inputs, the input ports, I've connected them to the switches. And all the output ports, I've connected them to the LEDs. If you want to use the 7-segment display, you will see all these numbers over here. They tell you about what each and every one of, how to connect them to the 7-segment display. Right now, just worry about those things. You don't know about all these things unless you take 3183. What these are, how to control the other things. But this is quite useful for doing any kind of testing that you have to do. Anyways, that being said, the manual which I've provided to you guys, I've taken the example of the prime detector. So I'm providing a 4-bit input, and if that 4-bit number is,
Yeah, just stop.
so do you still want to see something, or
Yes.
it will take me just a minute.
What time is it?
That clock like just stop. Says 10:15, so.
So you have to go to the Xilinx Project Navigator always.
Silence is expensive.
What is it?
I tried to buy it for a year.
The program? Wait, say that again. Did you?
$1,900 for a year.
Okay.
Okay, so
I
I've created this prime detector. What it does is, I've gone ahead and done all the generation of the program. When you do this generate program file, it actually creates something known as a bit file, and that bit file is what you're going to burn onto the FPGA. You have to open the impact management tool, just say no to this service, do a boundary scan, you have to go to the output, do a cable setup. All this is there in the manual. Oh, he's gone ahead. Okay. I can't do it. The Mosaic administrator has changed something. He has to run this command. I can't run it because I'm not the administrator.
Huh?
I'll tell you something in a minute. I'll tell you something in a minute after we get done with this.
I hope it's funny.
Sorry guys, I don't think I can show it to you right now, but if you have finished writing the code, you'd want to wait for maybe like 10-15 minutes after the class before you actually go ahead and do it, because I'm going to call the administrator and ask him to do this. I think it should not take more than 15 minutes for him to finish this work.
So this would stop us. This would stop us as well.
Yes, it's going to stop everyone. He has to go ahead and run this command from that library, and I don't have access to that library.
Oh, cool.
So, sorry about that.